not. This one has 0 missing. Okay. Let me just go to one example here. Let's just go to missing data now. So, with missing data, data that's not observed for various reasons, you need to be very careful. There are the following strategies, okay? If in this schematic that I showed you, if you encounter a case where one of the observations is NA, or missing, you can discard the complete case and go down to the second case to construct a complete collection of data that's available in its entirety. This is likely going to reduce drastically your sample size, sometimes by an order of magnitude. You can be working with 10% of your data if you keep discarding subjects. But that's not the worst part, because if you have 1 million records and you end up with 10% of 1 million is 100,000 records, that's quite a few records. The question is this still sound to do? And the answer is no, because the people that were missing may be the sicker people that never showed up for a follow-up training or something. And if you exclude all the sick people and only look at the people that are healthy or close to healthy, you're going to be having a significant bias in your inference at the end, right? Does everybody see that? So you got to deal with this missingness. There is multiple ways to deal with it, depending upon what is the cause of missingness. Is data missing completely at random? Is it missing at random, or is it known to not be missing at random? If the data is completely missing at random, if the data is completely missing at random, it's okay to start discarding the missing cases, because if you have large number of observations, obviously, because discarding them is not separating or stratifying different cohorts that do not get included, okay? But this is a very hard assumption to validate whether data is missing completely at random. It's very, very difficult. If it's missing at random, it assumes that the probability of missingness has a known but random mechanism. So you know what may be causing the problem, but you can only probabilistically predict who is not going to show up for a follow-up. You can't say Joe Schmo is not going to show up for follow-up. You can say Joe Schmo is 30% likely to show up for follow-up. You know, so everything is quantified in terms of probabilistic. And if it's not missing at random, well, you got to find out the missing mechanism and correct for it, because otherwise you're in uncharted territory. None of the theory works there. There are many mechanisms for dealing with missing data. So look at this example. We've already looked at, if you want to compute the mean of a variable and you want to remove all the missing cases, you can just use na.rm equals to true, which means the not available dot remove equals to true takes them out. And then if you can do the same thing for another variable, which is sanitation versus drinking water in our case. And then look what happens here, you guys. This is called imputation by averaging. Every time, so through all the 3,300 cases, we're going to have a for loop that cycles through all the 3,300 rows in the data set. If it finds a not available drinking water value, okay, it imputes it by the average for the drinking water where we excluded all the means. Okay? And similarly, for the sanitation, if it finds is NA equals to true, then it's going to impute it by the corresponding mean M2 of the sanitation where you excluded the missing values. So, at the end of this operation, the water imputed data set is not going to have any missing. Okay? Now, this is, so the first way of dealing with missingness is just to ignore them. You can only do this if two conditions hold. First of all, you have very large number of observations, and second of all, you have strong evidence to suggest missing completely at random. If you don't have these conditions, you may try different imputation strategies. The imputing by mean is one, very efficient, very fast, not the best strategy, because again, if you have some folks that have an interesting criterion in common and they tend to be more missing, then the majority that are recorded is going to yield higher values for these artificially. Is that right here with me? Okay, so you typically don't want to do this. So if you don't want to use this, there are multiple imputation strategies. Okay, one is called multivariate imputation package. You can load the library in, and the first time you do it, it's going to ask you to install it. Okay, so you can install it, run it. So what this thing does is it looks at the joint distribution, because remember, people don't have, well, the general situation is that people don't have one missing value. People have multiple missing values, okay? And it looks at the distribution not only of the missingness within features, but also the relation between the missing values and the different features. And then for each individual, it provides a uniquely imputed value. It doesn't replace all the missing the way we did earlier with the mean of the entire column. Is everybody here with me? So based upon the characteristics of the individual or case, it's going to impute the missing values using statistical theories that allow it to generate something that's unbiased. And if you recompute the means before the imputation and the column means after the imputation, they're going to be very consistent. So you're not introducing alteration of the distributions of the features when you do these imputations. And at the same time, you essentially try to find cases that have similar profiles, similar phenotypes, and observe how to swap and how to correct the observation that may be missing. So here's an example where, you know, we've essentially called the we construct a missing data frame out of the water data set, and then we are going to, you see it reports which ones of those have missing and whatnot. And then here is where you call multiple imputation. You provide the missing data frame, and then you say how many iterations and how many chains this needs to be done, and whether or not you want the algorithm to report at every step verbosely the status. So there's two important parameters here: how many chains and how many iterations. When you do imputations, most of the multiple imputation software does these things repeatedly multiple times. And the reason why it does that is after each iteration, it compares the distributions, the joint distributions of the raw data with missing values, and the first iteration of the imputed, make sure these are consistent, then takes another sample and repeats this, in our case, 10 times, and then averages the results of the values that were imputed. It averages these, and then it does this 3 times in a row. So at the end, believe it or not, you end up with 3 completely separate, complete data sets. You get 3 chains, okay? So you started with one data set that has lots of sporadic missing, and you end up with 3 data sets that are fully complete. So the question is, well, which one do I work with? Right? Okay? And there is 2 approaches for that. One approach is to out of these 3 chains of the imputed data set, you can kind of average them or find some kind of a central point, I suppose, and work with this complete data set. Okay? Another point is to apply your analytical protocol on the 3 chains independently, and then at the end pull the results, because your analytical methods are going to generate some kind of an inference. It's going to tell you, here is a linear model from the first chain about the relation between the individual's cognitive abilities and their phenotypes. From chain 1, we get model 1. From chain 2, we get model 2. From chain 3, we get model 3. And then you at the end aggregate, it's called pooling the results from these 3 complete analytical steps and generating a single inference at the end. For example, you may be averaging the effect sizes, the betas, the probability values, the likelihoods, whatever the result of your inference is, it gets averaged at the end instead of averaging the 3 chains before the analysis. Statistically speaking, this second algorithm generates more reliable and reproducible results. Anyways, I know this is a bit hand-waving, but there's a full example. You guys can work it out and see how it works. Okay, so this is another interesting syntax. Once the multiple imputation returns these data frames, they are lists. List 1 has chain 1, list 2 has chain 3, and list 3 has chain 3. So they're indexed by double bracket, and then which chain are you talking about, and then close the double bracket, and that's the summary. So you can report the summary for each of them, and then see if the summaries are vastly being changed for the chain 1, chain 2, or chain 3. You know, because if you see huge deviations in the variables that you imputed in the different chains, that's an indication that you've got a problem. They need to be pretty consistent. All right, jumping ahead. This is simulation of multivariate data. Let me skip over that. We looked at some simulation already. Okay, so when you deal with missing data, you should always plot the missing data plot. This kind of tells you, this is the best evidence you have as to whether your data is likely to be missing completely at random. On here, you've got the features are the columns, and then the observation number, the index from 1 to 200 all the way up to 1,000 gives you the corresponding cases. So look what happens with a real, this is a real data set where we removed at random 30% of the observation. So the black areas are the missing data. So you see how nicely spread out. It's almost like a random noise, isn't it? Okay. This kind of tells you that your missingness is stochastic in nature. It's not. I'll show you some examples later on where you see a big block of missing here would indicate that something is going on. It's not quite random. Now there are some blocks, big, but mostly, you know, black is intermingled with the orange. So you want to see these types of plots to indicate, and then this is the graphical way of determining whether or not your imputations worked well. So the gray, so for each variable, the gray histogram shows you the distribution of the original data with missing values. Okay? The blue shows you the blue curve shows you the distribution of the data after the imputation, and the red shows you the distribution only of the values that you artificially plugged in, of the synthetically generated values. Okay? So what you like to see here is you like to see these three curves be pretty consistent, right? Is that right, Hilden? If they're very inconsistent, you've got some kind of a problem. There is no match somehow. And you know, I mean, they're not obviously going to be at the same height, but you want to see the shape of these distributions to be, roughly speaking, very similar. So that's a diagnostic plot, and this is done for all the features here. Okay, there's another example. there's more of these examples. You can look them up. Okay, so here, right. So here is the original data missing pattern, and here is the average completed data. There is no more missing. You know, you're happy with this. This looks pretty stochastic, so this is good. Oh, and now here what we're doing is we're actually showing how to pool the results. In this specific example, I just want to do this thing real quick, just to show you the real situation of how things are done. One sec. Okay, here. So the pool method in R is going to fit the linear model. Each of the imputation chains, for each of the 3 imputation chains, it's going to fit in this specific linear model where, remember, we generated, in this case, 11 variables, x1 through x10 plus 1 response variable. So the pool method is going to fit in all these models, 3 models for the 3 chains, and then it's going to aggregate the results at the end. And here is your estimates of the coefficients and their standard error, right? So obviously, if the standard error is this big and the coefficient is this small, it might as well be 0, right? So this is not a statistically significant coefficient. And in this specific case, I know x7, I believe, was one of these variables which was real. The other ones were kind of fake. So you see, x6 does not contribute. x7 is very important. It's one very tight variance, and some of the first ones are right. So x1 is close to 1 and very tight variance. So this is definitely an effect, a very important feature. This one is not. x3 is not, because the variance is too big relative to its estimate. So this is in a way a validation, if you want, of the imputation with synthetic data. And now here is one example with a real data set. Traumatic brain injury, TBI. So you can look at this case study. There is a very nice description on the website. Again, loading the data first, summarizing the data. You see there are not very many, but there are missing, as you can see. Occasional things. In this case, this was a very interesting case. We wanted to predict using cognitive Glasgow scales and various other and imaging results. We wanted to predict whether somebody would have seized, whether somebody have had a seizure or not, based upon the type of head trauma, the injury, based upon various cognitive scores. We wanted to predict whether or not the individual is going to have seizure. So, but we have to complete the data set before any of that takes place. So after you read the data in, you construct a missing data frame, which is going to be fed into, okay, well, first of all, you do the image of the missingness, and then here is a little bit of a 7 missing patterns it reports are observed. Here is the reason for missingness. You see how this is not a random pattern of missingness. Okay, should be clear to everybody. The data is very concentrated. For these features, these are the EEG spikes, mean per hour, max per hour, for quite a few of the subjects between 25 or so and 42 or so. All of these guys had these missing. There were a bit missingness here. I'm not too concerned. And the last subject had some of these guys missing. So this is the block that's the problem here. So, all right, so we're going to examine the missingness before we do the imputation. So let's go ahead and report some of these summaries. And then here is where we do the multiple imputation with 5 chains in this case, and again, some of the diagnostic plots, you need to examine this. They're not terribly, because there is so few missing in this case, it's not too bad. The important thing is that the gray and the blue coincide well, which means that the imputed and the raw data set were kind of relatively comparable. Okay? And then we are going to extract in these data frames the 5 different imputations. They're going to be indexed, remember, with these brackets. And here is the lapply function that generates a summary of all of the 5 chains by saying chain 1. Remember, this is the first complete case. And then you report all the summary statistics, and then chain 2 is going to be right below it. So if any one of the variables is of interest, you should pay special attention to this variable just to make sure that something is not too varying between the different chains. Chain 3 and 4 and 5 should come next. That's 5. Okay. And this is, by the way, if you want to save, sometimes you want to impute the data and you want to save out these data sets for further processing. You know, you may want to send them to somebody, you may want to come back a week later or something, so that you don't, because imputation is going to take time. If you have a large data set and you have a lot of iterations and a lot of chains, it may take, you know, depending upon the data set, from 1 minute to 2 days. You know, so you want to save these things out before you close the session. And then here, you guys, is where we are going to be fitting. Look at this, you guys. A generalized linear model predicting whether or not the individual has ever had a seizure. Presence or absence of a seizure is a logistic regression kind of outcome variable, because it's binary, either yes or no. And then you're going to use as predictors of seizure the type of surgery that they have undergone after the trauma, and then the worst Glasgow cognitive scale. Maybe you want to factor as the gender. Why? I mean, I don't know, because different body sizes, for instance, right? Men are prone to take a lot of hits to the head and still continue to march on. They may not be marching in the right direction, if you know what I mean, but they're going to be marching. So, and then age obviously is a huge variable to when you study trauma, right? Simply because of the nature of the injury. And then look at this. Then you specify that the data is the data frames chain 1. So I'm only fitting a model to the first complete instance of my data set. A generalized logistic regression model to predict whether or not an individual is going to seize. And then binomial. So the summary is what I was trying to say, can be applied. Remember, we did summary on data sets, but here it's applied to the first linear model. And it's going to report for you the R squared, the coefficient of determination. It's going to report for you some of the estimates and whatnot. To the very end of this, where we actually compare, remember, in this case, we imputed 5 complete sets of the TBI data set, okay? And the corresponding effect sizes are reported for the 5 chains. So look what's happening here. You know, the ID has nothing to do with it, right? You know, the corresponding means, so these are pretty consistent. There is a bit of variation here in the field Glasgow Coma scale. Well, you know, pretty consistent, I guess. These are pretty consistent. So you can see that the results are pretty consistent. In other words, all the chains tend to be tend to generate the same results, which is encouraging. And remember, what was the variable with the most missing is the spikes HR, was it? Yeah. Okay, so you have 32 in one chain, 30, 49, that's rather large, 68. Look at this chain. The fourth chain was twice the mean value of what we had in the first chain. So that's a bit of a concern here. Remember, more than twice is a point of concern. But the other ones, they're, you know, this one is a little bit underestimating. The other ones are 30, 30, 49 is large, 68, well, it is what it is. So that goes to show you that indeed which chain of the complete data you're going to take will significantly impact the results. Is that right here with me? So you can't rely on a single chain because you can actually pick the one with the highest or the one with the lowest, and then your results are going to be very biased. So that's why you typically would fit the model on each chain separately and then try to find out how to aggregate the results at the end. Okay, so I'm not going to talk about the H-hat convergence here. All right. Now, is anybody ever in the need of, okay, let's just skip over this. If you ever have to download data from existent websites, including the soccer, there is an example of how you can get some of our data that appears in wiki pages, literally tables, large tables, but embedded in wiki pages that might have multiple tables, right? One table is with the data description, one table is with the metadata, one table is with the raw data. So there's lots of tables in HTML pages. Here is an example of how this can be done in R. Very, very simplistically, you essentially say, parse the entire content, the div content of the HTML, parse it, find the starting and ending tags for tables, load these as table 1, table 2, table 3, and then specify which table are you interested in parsing. And now you have at the end the earthquake data, in this case for the large earthquakes exceeding 5 on the Richter scale for the past 100 years in California, I believe. So this is just an example of how you can read. And now that's an interesting example, because this shows you how to generate 3D surface plots in R and kind of navigate, right? So this is the way you look right now, is the Californian coast. So let's see who's had geography lately. Longitude and latitude, all right? The longitude at 0 goes through Greenwich, through the UK, right? You guys are here, Malaysia. I was thinking about it last night. Malaysia must be what? 120 degrees east of Greenwich? Does anybody know how far?
Something like that.
Yeah, right. Plus 8 hours should translate to something like 110. I thought it was more like 100. Anyways, so we are about 110 degrees east of Greenwich. Now, California is 120 degrees west of Greenwich. Okay? So let me just move the mouse out here. And look at it right from the top, kind of like this. So if you guys can picture, this is kind of the Californian coast here. This is San Diego and Tijuana, Mexico, and then this is LA, and this is Northern California, San Francisco, and then it goes up. And this is the corresponding parallel, the latitude. And let me see if I can. Okay, that's. Okay, so let me see. I need to rotate it to. Okay, that's. Sorry. This is Southern California, this is Northern California. 34th parallel north, okay, 34 degrees north. Malaysia, I honestly thought Malaysia was in the southern hemisphere, but it's 3 degrees north. Kuala Lumpur is 3 degrees north of the equator, right? Am I right? 3 degrees, okay? So we're still in the northern hemisphere. LA is about 36 degrees north or so, and these are the renderings of the frequently occurring earthquakes exceeding order of magnitude 5. Okay? So the density of these earthquakes is what's shown here. And this is a pretty cool plot. You guys can easily regenerate this and zoom in and kind of navigate directly in the browser, which is a very unique feature of R. So let me see. Using kernel density and Plotly. So Plotly is another package that you need to get for some of these. And the basic idea is that this kernel density computes the frequencies of how many times were longitude and latitudes for certain magnitude earthquakes recorded, and then the density, the kernel density, the two-dimensional kernel density that you see represents high frequency are high and low frequency are low, obviously. So the hot spots are in northern and southern California where earthquakes are prevalent, the San Andreas Fault and so forth. And I think later on I'm going to show you neuroimaging examples with the same tool with Plotly. Yeah.
I have been using kernel density estimation.
Pardon me?
I am using kernel density estimation.
You don't have to. You don't have to use kernel density estimation. I do because the data comes in. If you guys look at the data, right up here. Let me show you very quick. Okay, and this is more of a map kind of that I show you. So Southern California, Northern California, and here is the data. So the data has longitude and latitude. So you essentially have points in space, and to generate the surface, think about that. To generate the surface, what is the surface represented? Because the surface cannot possibly represent an event occurring or not, right? It's going to be just sparse spikes, right? Event occurred, 3-4 miles, another event occurred, right? And you can smooth these things as well, that's what we're doing, but you need to compute a two-dimensional probability distribution of the frequency of these events. And that's where the kernel density comes up.
So kernel density estimation is a parametric or non-parametric estimation?
It is parametric, yeah.
Parametric.
Uh,
I think it is non-parametric.
That is a good question. I thought it was a mixture of Gaussians, but you may be right. So we need to look at this. It may be non-parametric. That's right. It essentially, what it does, you guys, is it takes a lens, walks through the entire space, and counts how many times did I see something in the lens, and this determines the height of my surface plot. That's what it does. Now, I think you may be right that it's non-parametric because there isn't a finite number of parameters that it estimates. So it probably isn't. Okay, so again, I'll show you some very interesting examples later on, especially one interesting example where, I don't think it was in this chapter, I think it's a little bit later. All right, and these are a variety of 2D, 3D, and this is also interactive. 3D scatter plots. Scatter plots are great. In 2D, everybody has seen scatter plots, right? In 3D, they're difficult because they overlay each other, okay? Just like in the brain surface that I showed you. Remember how I had to change the opacity of the brain surface to pair in and look inside of the tracks? Because if you make the thing opaque, the skull and scalp, you're not going to be able to see what's underneath it, right? Here it's the same problem, but what saves you here is that you have a third dimension, which in our case is the motion dimension. And the motion dimension untangles ambiguities that are seen in a static image like that. So if you were to publish an image like this, it's going to be horrible. Nobody's going to know what is going on. But if you have this interactively and you rotate it, and now, boom, here's the Californian map. You know, just like I showed you a second ago. Look at the resemblance, you guys. Look at the resemblance of the hotspots here and here, and what we have over here, right? And then once you do a little bit of this, and now the magnitude, the beauty here is that the magnitude is in this azimuthal direction. So you see magnitude 7, I can pinpoint exactly where they occurred. See? 7.39, it occurred at, that must be San Diego, incidentally. That far low, right up here. Yeah. This is way down south. And here is another one. This is probably the Great San Francisco earthquake, etc. Okay. So, anyways, Plotly is very helpful here. Here is another example of heat maps. Okay. And now here is the question with. This is also interactive, by the way. So look at those if you're interested in doing visualization that involves surface renderings. Here is an example to keep in mind. 600 volunteers in total, 434 are patients, only 166 controls, and only 61 in between. Very unbalanced data set. Everybody would agree with me, right? Why? Because you look at two of the groups, and if the sample sizes are twice or more different, you've got a problem. 61 fits into 408 times. So you've got a huge imbalance. So what happens here? Well, you can work with the data the way it is, or you can use synthetic minority sample oversampling to rebalance the groups. The basic idea is very elegant, but you have to also be careful with this tool. The basic idea is very elegant because it looks at the samples, finds the smaller samples, and then it says, well, obviously I'm not going to be reducing the larger samples to the smaller sample size, right? You're going to be upsampling the minority samples. The question is, how do you do that? And the answer is, well, you look at the distribution just the way you do imputation. It's almost like imputing, but you impute cases that are not present at all. They're just no, 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 all the way across. So you're trying to impute these cases, and the problem with this technique is called SMOTE, S-M-O-T-E, synthetic minority oversampling technique, is that if you have only a few cases of the minority sample, something less than 10, when you upsample these to, let's say, 100 or 200, you're going to get a lot of repeats of the same individuals. In this case, 61, the smallest sample is small but not exuberantly small. I can easily triple the size of this to about 180, maybe 200. And this is going to be pretty safe. But if you have, again, less than a dozen observations, it is a problem to upsample the minority. Okay? So here it's shown what the basic idea is, that you use the SMOT package right up here, and the package is called unbalanced, and here is where you do the upsampling of the minority. You provide the X and Y, the inputs and outputs, and then percentage coverage and various other parameters. And what comes out of it is groups that are, roughly speaking, not exactly the same size, but roughly speaking comparable. Again, the oversampled population is not going to be touched, just the underrepresented are going to be quote-unquote imputated, or synthetic data is going to be generated for additional subjects. And you can do, for example, what kind of validation should you do once you upsample the minority cohort? Well, you got to look at are the distributions of different features changed by what you did. So in other words, if the mean of the minority sample was 50, after the resampling you're at 60, you've got a problem. You know, if too many cases remain the same, you've got a problem. So you got to inspect a little bit of this. I've just shown you a couple of examples here where you can use parametric and non-parametric tests to look at the adjusted p-values, report these p-values, and essentially draw the corrected versus raw p-value plots, etc. So the last two things here we're going to skip over. One has to do with dealing with SQL data. For those of you that have used data stored in a remote database, typically, either SQL or no SQL database, relational or non-relational databases, R can deal with these as well very elegantly. Obviously, most of these are authenticated. You need to have access. You need to know the SQL query language. You know, there's a little bit of background that you got to do there, but there is a way to handle data that comes from SQL.